Good morning, calculus. Well, calculus, always thinking into the future. Pre-calculus students. Um, guess Mother Nature's going to send a little more rain our way. Fortunately, we're not in the direct path. I think that's been a blessing. Um, we don't like the rain, but at least I think we will maybe have a little less rain than we had with the last storm. Hopefully, that still doesn't give much relief for the residents of Louisiana that have just been pounded this year. Um, we're lucky. So if you're out and about tomorrow, please be careful. We'll have plenty of rain, and if you have to drive, please slow down and be very safe. I have to do the same, so I'm just passing along what I try to do myself. Now, for our test this week or next week, I will post an announcement just to kind of give you the basics, the window of time. It'll be very similar to the last test. I believe that it's good to give you that space of time to pick a optimal time for you to test where the stress is low, where you feel comfortable. And that's one of the benefits of having the online setting. And I believe that even though we meet at a class time, I still want to afford you that so that you are at your best when you test. There's plenty of information, and high stress is nothing that anyone needs right now. So, good with that. What I want to do today is to talk about the unit circle and circular functions. These topics on the surface will seem very, very simple, but it builds really quickly, and the basic ideas we have to all put together to come up with some unified way of talking about circular functions. And the genius of Dr. Stewart's book is that he starts with the unit circle, which is really the place to begin. So I want to share my screen with you. So the idea, ladies and gentlemen, is that when we begin the study of trigonometry, and you may have seen some of this in a previous class, and that's fine if you have, or if you haven't, it won't make any difference. I start at the beginning, and the idea is we want to first address the unit circle and how we build trigonometry from that. And then in the next chapter, we will impose the right triangles on the unit circle and build a different interpretation of trigonometry. And so the the nice thing about trigonometry is that depending on what you're studying, you may have a definition that supports that line of study. If you're in an analysis class, you may define the trig functions in terms of infinite series. So it just really depends what you're doing. What we try to do in the pre-calculus is describe the trigonometric functions and the circular functions, so to speak, utilizing geometry that supports the work that you do in calculus and will support the work that you do in science, uh, especially physics and engineering. So I think, don't think that a bunch of smart people got together and thought this up overnight. These are conventions that have been laid down over many years, and they've proven to be very successful. So what we want to do is just start with some basic ideas so that you understand Professor Ron's unit circle. It's not mysterious. Everybody thinks it's a very mysterious object, but it's anything but that as long as we set the groundwork for it. So I went ahead and wrote down a couple of things that would help us to lay a foundation. The unit circle is exactly what we think it is. It's the set of ordered pairs. And again, we have the basic definition of a circle with center 0, 0, the origin, and radius 1. So that's just x squared plus y squared equals 1. This will create tons of identities for us. Everything that we have in terms of trigonometric identities can all come right back to this. And it's amazing that S1 is what gives life to all of this mathematics. Now, when I say S1 here, that's what we call the one-dimensional unit sphere, and that will be often a symbol that I use for the unit circle just to save time. So I'll say S1, you think unit circle, and S1's a whole lot quicker to write than unit circle. So we'll stick with that. That is a common notation in mathematics. Now, how do we address what you've seen on a unit circle? We start out this way. We measure distance along the unit circle from the point 10 using pure numbers or radian measure. That is, when you look at the unit circle, we're going to think of starting here and measuring the distance in a counterclockwise way like this. That will be called positive measure. And then we can think of starting at 10 and moving in a clockwise direction, and that will be negative measure. And then, well, for right now, just don't worry about the degree symbols. We'll forget those for now. But you see all of these multiples of pi here. And then you see these terminal points connected to these distances marked off by these fractions of pi. Why is that? Well, let me show you why the unit circle looks like this. Now, the pi's come from basic geometry, and we all love geometry because geometry bails us out of all the difficult problems that we have in pre-cal and algebra 1 and you name it, and even in calculus. So when you consider pi, which is the ratio of the circumference to the diameter of any Euclidean circle, you come up with a formula that says that the circumference is 2 pi r. But we start with a radius of 1. So the distance around the unit circle is just 2 pi times 1, or 2 pi radians. Now, when I say pure measure, pure numbers, we mean radians. And when we say radians, we're not attaching any kind of dimension to that. That's just the common usage. So when we say radians or just a number, that means no dimension, pure measure. And that's why radians are basically how we consider trigonometry in calculus, because the radian measure is the natural measure of the real line attached to the unit circle. So we love our degrees, and when we talk about it, they're fine, but they're a human invention. They're basically what we decided to do to make our lives easier, but they don't have the connection to the real line like the radian measure. Now, one thing that students maybe overlook when they think about the unit circle is the following. And what I've written here is we subdivide 2 pi to make convenient units of measure along S1. And like I said before, as we move counterclockwise, we call that positive measure. And as we move clockwise, we call that negative measure. Now, ladies and gentlemen, these are just conventions to mimic the real line. So again, this is not something that's proven. This is taken as convention to mimic our real number line. And we can almost really think of the point 10 as the center of our real number line, the 0, so to speak. Now, what I've done here for now, and this is a really nice symbolism that Dr. Stewart uses, we will represent distance along the unit circle with the lowercase t. Later on, we'll use x, y, t, theta, phi, whatever. But right now, what we want to do is have a letter that's different from x and y. And so this is what the author uses. And I think it's a very nice convention and one that helps more understanding. So what I want to do first here is I just want to write down 2 pi with some convenient multiples, so you can see where these numbers originate. And then, of course, I'm not going to reduce them for now, but I want you to see where these actual fractions of pi come from. So we can start with 2 pi divided by 12, which at this point, the 2's absorb, and that reduces to pi over 6. So we're thinking if we take units of pi over 6, we can see the first unit here, 0 to pi over 6. That distance is pi over 6 right there, from here to there. And so you're thinking, what if you just went it around in units of pi over 6? Well, you can see that we can do that. Now, what are those actual units? Well, you just simply start with 0, pi over 6, 2 pi over 6. Don't bother to reduce right now. 3 pi over 6, 4 pi over 6, 5 and 6 pi over 6. 6 pi over 6 is pi, and then we just keep going to 12 pi over 6. So you're going to look on the unit circle, and you're going to see denominators of 6, and this is where they come from. Now, of course, these will coincide with some other fractions of pi, and we'll just write those in the least common form, that is reduced fractional form, just for the utility of writing the unit circle. We all know that when we add fractions, the denominators need to be aligned. And so maybe the unit circle might look nice, but it's not always very user-friendly. Now, the next division of the unit circle that has become convenient is 2 pi divided by 8, which gives us pi over 4. So here we can think of moving from 0 to pi over 4. This distance is pi over 4. Notice as we terminate, as the distance t terminates, it has a corresponding point on the unit circle. That's called the terminal point. And you might be thinking, why are these terminal points this way? And then it's like the circle has all this magnificent symmetry. If you learn these terminal points, you automatically know the terminal points for the rest of the circle, because you have origin symmetry, you have x-axis symmetry, and you have y-axis symmetry. I mean, you've got all the symmetry that's possible. So again, we're seeing that maybe this unit circle is not so complicated as we might have originally thought. So when you consider the pi over 4, we just move along the same way, ladies and gentlemen. 0, pi over 4, 2 pi over 4, 3, that's the pi, and then up to 8 pi over 4, which again is 2 pi. So again, we get some overlap, but we generate some very convenient units of fractions of 2 pi, which turn out to be very useful. Now, the next few are very simple. We divide by 6 to create units of pi over 3. And so in that case, you're thinking, well, that's just 2 copies of pi over 6. If you start here, go pi over 6, then another pi over 6, that gives you 2 pi over 6 or pi over 3. So this distance is pi over 3. And then, of course, we can move around pi over 3 again, pi over 3, pi over 3, pi over 3, and then pi over 3. And so what are those measures? Well, we can write them down. Just again, proceed 0, pi over 3, 2 pi over 3, to pi, 4 pi over 3, 5 pi over 3, and then to 2 pi. And we see these right here on the unit circle. Now, after that, it gets pretty simple. We're thinking when we're in the quadrants, we're away from the axes. So if we want to end up on the axes, we divide by 4 and we get 0, pi over 2, pi, 3 pi over 2, and 2 pi. So when we think about the axes, 0, pi over 2, pi, 3 pi over 2, and back to 2 pi. And then lastly, you're thinking, well, don't you want to stop now? It's kind of obvious what the deal is. Well, we could divide the unit circle into 2s and have what, 0, pi, and 2 pi, and then not divide it at all and just have 2 pi. So the idea here is that the unit circle has certain divisions of 2 pi that turn out to be very useful. They give us very useful terminal points. And then when we compare the pure measure to our invention of the degree measure, again, we get some really nice triangles that you remember from high school geometry. So the idea, ladies and gentlemen, is that the mystery is no longer. These are just convenient multiples of 2 pi that serve us well. Now, so you're thinking, if we lap the unit circle, we've run or walked, so to speak, a distance 2 pi. And you're thinking, okay, so we're really going to mod out by 2 pi. I'll say a little more about that. But what I did was I wrote down a little unit circle here and thought about, okay, well, if 0 to 2 pi, and then we go again, we're getting these units of 2 pi, which is really, we're starting at the same place again. So we're getting repetition that really is going to make our life a lot easier. So we're thinking, when it comes to terminal points, that if we can figure out the terminal points here, I mean, this is an easy one. That's just 1, 0 and 0, 1 because it's the unit circle. But what about these 3 points? So once we have these 3 points, we automatically get the points across, down, and then through the origin automatically, just using symmetry. And so you're thinking, well, how were these determined? And what I've done is I've written down some very simple algebra here that I want you again to demystify the unit circle. So I started with the simplest one, which is just pi over 4. That's just well, you're thinking, Professor Ron, that looks like the line y equal x, and you're exactly right if you think that. But we kind of proved that. So for instance, what we want to think about is this point P, and we want to compare it to the point B, which is 0, 1, and the point A, which is 1, 0. So now what we're thinking is in terms of distance, if we measure this chord and we measure this chord, they would have the equal arcs of pi over 4, and therefore the chords that subtend the arcs should also be in equal length or be congruent. So what we're going to do is simply say, okay, if we start on S1, we can say the distance between P and A here, P and A here squared would be the distance between P and B squared. We don't need the square root, so we square it. I put the little 2's right there. And so then you do your little trick with the Euclidean distance, the x minus the 1 quantity squared plus y minus 0 quantity squared, which gives you this. And then, of course, the same here, x minus 0 quantity squared just gives you x squared. And then y minus 1 quantity squared gives you that. These are equal. Again, the distances are equal, so the squares of the distances are necessarily equal. Now, of course, we're thinking, well, this is algebra 1. This is simple algebra. We reviewed all of this. You expand the binomial to get x squared minus 2x plus 1. Same on this side, you get the y squared minus 2y plus 1. But we live on the unit circle, so we're right here. So any copy of x squared plus y squared will give us 1. So x squared plus y squared is 1. Add to 1, we get a 2. And we're left with a negative 2x. Now, if we look on the other side of the equation, we have the same thing. X squared plus y squared is 1 because we live on the unit circle, and then 1 plus 1 is 2. So you're thinking, okay, well, now the 2's absorb, and therefore the negative 2's absorb, and we're left with what you thought when I did this. That is, this is just x equal y. Now, okay, so basically you're saying that the x and the y coordinate here of this terminal point are equal. So what is that point actually? Okay, well, you go back to the unit circle and you replace y with x. So that gives you x squared plus x squared. So that gives you 2x squared, which is equal to 1. And so now we basically have the square root property, our friend, the square root property, x squared equals 1/2. But now we're in the first quadrant where x and y are positive. So we're going to select the positive square root and get 1 over root 2. Now, if you look at Professor Ron's unit circle, you'll see things written as the square root of 2 over 2, which is the rationalized form of this. I have no appreciation one way or another how you write it. I mean, that's up to you. I happen to, though, prefer this method of writing it because it makes computation easier. When you just have a 1 over root 2, that's easier to manipulate. But I've coded my unit circle with rational forms just because this is conventional. But you can always go back and switch this. What I did last year was add the degree measures because my students got mad at me that I didn't have degree measures on it. And I said, well, you can figure that out. And they said, well, could you just code it that way? So I went back to my program and put in the degree measure. But don't worry about that right now. So we have that terminal point right there. So we have 1 over root 2, 1 over root 2, or root 2 over 2, root 2 over 2, however you want to write it. Now, so again, if we have this terminal point, we've got that one, we've got that one, and we've got that one automatically. Now, the only thing we have to do is to assign a negative if it's necessary. Here in the second quadrant, x is negative, y is positive. So we would have to put a negative on the x coordinate for this point. For this point, both of them would get negatives. And for this point, the y coordinate would get negatives. So the idea here is with this nice symmetry, you're thinking, why do we just pick these points? What's so special about them? Well, they occur a lot, and of course there would be other exact terminal points that we can come up with, but they're a little bit more complicated to write, and they crowd the circle. So I think this has been distilled to the standard unit circle, and we'll go with that. Now, the next one would have to be pi over 6 right here. Now, this is not as simple, but we can set up a routine that's just like this routine. So what I've done here is I take the point Q here, which is the terminal point of the distance pi over 6, and I just label that Q with coordinates X and Y. Now here's how we do this. If we move down pi over 6 and another pi over 6, that's actually pi over 3. And I want to label the point right here, which is directly below. Well, the X coordinate would be the same, but this is basically reflection in the X axis, which would make the Y coordinate. If that's Y, this becomes the additive inverse of Y, okay? And then I'm thinking, well, the distance squared between Q and R should be the distance squared between Q and D, because they are both subtended by the circle measure pi over 3. So this distance would be this distance. Even though my circle's not drawn very well, you can use your imagination. So now, just like we have here, we just do the Euclidean measure. So with the Q and the B, we'll do X minus 0 quantity squared, which is this. And then we do Y minus 1 quantity squared, which is this. Now for the Q and the R, we do X minus X, that'll just zero out. And then we do Y minus a negative Y, so we get Y plus Y. So you're thinking, well, this is easy, and it is simple. And if you've never seen this before, that's unfortunate, because it's a very simple application of distance. And so now we get 2Y quantity squared, which is 4Y squared. Of course, this is 0. And then on this side, we just expand the binomial. That'll give us Y squared minus 2Y plus 1. So back to our friend S1, X squared plus Y squared is 1. 1 plus 1 is 2. So we get 2 minus 2Y equals 4Y squared. And then, of course, you know, we factor everything to death. We've got extra copies of 2 hanging out. So we divide by 2, we get 2Y squared, and then we'll get a negative Y plus a 1. Now, what's nice about this particular quadratic is that if we retire everything to one side, the AC method works. That is, if we do 2 times negative 1, those two, Z and W, they sum to 1, which is the coefficient of Y. So we get a nice simple factorization, 2Y minus 1 times Y plus 1. Now again, remember, our Q is in the first quadrant, so X and Y are positive. Now, of course, we're getting a value here of negative 1 from this factor, and it's not incorrect. It will give us a correct answer, but it's not the Y that we need. It's another Y. So we're not interested in that. It's not that it's bad, it's just not helping us with the first quadrant. So we select the 1/2. Okay? So again, our setup and our hypothesis kind of direct us through the algebra. And then of course, we go back to our S1 here and say, okay, well, if Y is 1/2, we can simply solve for X squared. That'll just be 1 minus Y squared, which we have here. And so we just substitute Y 1/2 in for Y. We square it, we get 1/4. 1 minus 1/4 is 3/4. And then of course, with the square root property, we get the square root of 3 over 2 plus or minus. But again, we're in the first quadrant, and so we know that Y is 1/2, so we will select the positive square root for the X coordinate. So now when you look at your unit circle and you look at the terminal point for pi over 6 radians, it will now be square root 3 over 2, 1/2. Now you're thinking, do we have to do one more? No, because we're going to be lazy. We're going to use the x equal y, and we just simply reflect this point in the line x equal y because they're symmetric about this particular line. And so the x's and the y's flip. So we get the point t, which is just the flip of this point. So we get 1/2 square root 3 over 2. So now, when you look at the unit circle, you see exactly what we just computed. The 1, 0 and the 0, 1 basically evolved from the definition of unit circle. We got those for free. These are on the axes, okay? This is quadrant 1. We determined this point first, then we determined this point. That is the terminal point of pi over 4 radians is 1 over root 2, comma 1 over root 2. And the terminal point for pi over 6 radians is root 3 over 2, comma 1/2. And therefore, the terminal point for pi over 3 radians will be the flip of this, 1/2 square root 3 over 2. So this kind of demystifies the unit circle. That's why the unit circle looks like this. Now, like I said before, these have been selected because they are useful to computation, and this has become what we call the standard unit circle. And so, again, I guess you could make up a unit circle that had more information if you wanted. A lot of times students will take the unit circle and they'll start drawing in extra stuff. And then what most people do, they turn over and they start writing down identities. So I've had students that have taken this and it's been like a book. I said, you should publish this. They have everything they need on Professor Ron's unit circle. I even had a student when I first started, he was convinced that I found this on the internet. I said, no, I coded this. So he kept looking for it because he wanted a new copy. Well, he never got the new copy. And even when he became an engineer, he still had this tattered piece of paper of Professor Ron's unit circle. I guess he thought that it was good luck and that he should not dispose of it, even though it was in a fairly dilapidated state. So the idea, ladies and gentlemen, is that this is your unit circle. You can use it. You can use it as a reference as you test, as you do your work, just to make your life easier. That's what it's for. And so use it to good health. So now what we want to do is look at some ideas like, what are we going to do with all of this? And this is the next thing I want to talk about. When we do basic computations, we're going to do some examples here, but I just wanted to go ahead and give you the idea of reference number. Now, with the unit circle, we're going to define the circular functions, but first we need to be able to work with modulo 2 pi, and we need to be able to work with reference number. Okay, so what we're going to do is we're going to take some real number t. That is, it will correspond to a measurement along S1. Maybe it's positive for the counterclockwise, maybe it's negative clockwise. So basically what we're seeing is that we run distance on the unit circle, we're basically mapping out the real line. It's amazing. The first interpretation of trigonometry via the unit circle is the only interpretation. If you want to see the significant connection between the real line and the trig functions. Otherwise, it's completely lost if you try any other method. That's where Dr. Stewart, that's where his genius has made his book superior. And when students say, well, I like it this way or whatever, I said, that's fine. You'll never understand it if you only think of trigonometry in one interpretation. So what we want to do, and I'm going to use his notation. I often make up my own, but he has a good notation. We're going to define reference number, and he uses the notation T bar. Sometimes you do like a little hat or whatever, whatever. I mean, I don't even care if you don't call it T hat, just have some notation for it. I'll use T hat for reference number. Now, what is the reference number? Well, you can think about it by looking at the unit circle, or in a better way, you can think about it by looking at it arithmetically. Okay, what we're going to do is all the t's that we consider must live in one of the 4 quadrants. So when you think about the quadrant, well, here, let me go back to the drawing. Your T must live in one of the four quadrants, either 1, 2, 3, or 4, with the given signs that I have here. X, Y, and all of them. Okay, that's a hypothesis. And then we want our T-bar to live in the first quadrant. Get a little refocus. And so in order to do that, we're going to define our T-bar this way. The T's live in these quadrants. That's a must. And then if T is actually in the first quadrant, T-bar is T. So that's the formula. So if you get pi over 4, then you're done. The T-bar for T equal pi over 4 is pi over 4. It follows this. Or maybe some other, maybe you have 2/5 pi, which is in the first quadrant, but not on the unit circle. So now, what if T lives in the second quadrant? We use the following formula. That is, we subtract T from pi radians. Again, this lives in the first quadrant. So these are just formulas. Sometimes Dr. Stewart says it's the minimum distance. The minimum distance is fine, but it relies on a picture, and a picture is not how we want to reason all the time. We need a diagram when it helps us, and we will certainly use them. But here, this definition is actually better for us. Now, if T terminates, so to speak, you think of T and the terminal point coinciding. If T terminates in the third quadrant, that is when we draw it, we're living in the third quadrant. We will define the reference number to be T minus pi. Again, that will put us in the first quadrant. But of course, we're always making sure that we are respecting the sign of X and Y in each of the quadrants. We'll find that out with the circular functions. And then of course, if T terminates in the fourth quadrant, we will define the reference number, T bar, to actually be 2 pi minus 2. So this is just a little recipe for computing T bar, or the reference number. Now remember, the axes are just that. They're like the boundaries of the quadrants. They are not in the quadrant, so to speak. When we say that T lives in quadrant 1 or terminates there, it's between 0 and pi over 2. So when you're on the axis, that's a much simpler case, and we don't really refer to that as being in a particular quadrant. That's just the boundary of a quadrant. And then of course, quadrant 2 will be pi over 2 radians to pi radians. And then quadrant 3, just using your unit circle or thinking about what we've done so far, will be pi to 3 pi over 2. And then quadrant 4 will be 3 pi over 2 to 2 pi. Now, you're thinking, well, how do we abide by this? Well, here's what I've written in red. And this is very important. Multiples of 2 pi are really zeros. Because for instance, if you have a T and it's got a copy of 2 pi in it, you're really starting here again. So you can basically equate that copy of 2 pi to 0. Now, if your T has no copies of 2 pi in it, then you don't have to worry about it. If it's already positive, you're done. You can figure out the quadrant. Or if it's negative, you can add 2 pi to make it positive and figure out the quadrant. So the idea is if you added negative 10 pi to a T, it wouldn't do anything, because you're just going to go counterclockwise 5 times and you're going to be right back here. So you will have not added anything of consequence to that T, because the 2 pi is the cycle length of the unit circle. Later on, we're going to call that the period of certain trig functions. So again, what we want to do is we want to compute modulo 2 pi. That is, any integer multiple of 2 pi, and these 3 lines mean congruent, will be replaced with 0. So that will help us as we do our computations. It's kind of like if you've already worked with 360 degrees or and all as being equivalent to 2 pi radians. That's the same thing. Adding multiples of 360 degrees to a degree is not going to do anything to it. That's a complete cycle. So you're back where you started. So that's the concept that we need to talk about here so we can have this. Now let's look at some examples. Now, we'll start out with some basic ones, and then I'll show you some simple techniques that will make this very doable. So for the first one, let's see here. Let's start with this one. We got an example here. 7 pi over 6. So t equals 7 pi over 6. Now, remember, folks, we can have the nice multiples of the unit circle, and of course, we can have multiples that have pi's in them that aren't on the unit circle, and then, of course, we can have t's that don't even have pi's in them. So we have to, work with some ideas to make sure that we keep everything, configured properly. So what we want to do is compute t bar. So when you look at this, you think, okay, well, first, where does t live? Note that we can say t equals, if you want to divide by 6, this is going to give you, for instance, 1 pi plus pi over 6. So we get 1 copy of pi plus pi over 6. So that's just like saying 7 over 6 equals 1 and 1/6. So I just put the pi's here, pi plus pi over 6. Okay, well, pi takes us to the axis, and then the pi over 6 pushes us into the third quadrant. So t lives in the third quadrant. So we can just think about the axes, 0, pi over 2, pi, 3 pi over 2, back to 2 pi. So this allows us, just with this simple calculation, to figure out where t lives. And so now, using our formula, this implies that t bar will simply be, in this case, t minus pi, using our formulation. That is right here, t minus pi. So we've already written t this way, so let's be lazy and just write it as pi plus pi over 6 and subtract pi. And that just gives us pi over 6. So there's our reference number, so to speak. So when we think about this, and then you're like, okay, Professor Ron, this is the unit circle, and we know what the terminal point is. So let's go ahead and write it down. So the terminal point, we've already computed because we know our unit circle will be what? Square root 3 over 2, 1/2. So we say this just basically corresponds to t equal pi over 6. So when we say that t terminates in a particular quadrant, as we write here, we just say that the terminal point lives in this quadrant. So that's how we get the correspondence and make our work a little bit more efficient. So again, you can just commit your unit circle to memory and do all of this from that aspect. But when you don't have a radian measure or a value of t that's on the unit circle, you've got to use your formulas. So maybe it's better to practice this way until you get really comfortable with it, and then you can mix and match the two techniques. So now let's look at this. Say we have an example where we're interested in t equal negative 11 pi thirds. And again, we want to compute t bar. Now again, remember, we might think approximately at times, but all of these reference numbers are given exactly, no approximations. Unless WebAssign says give an approximation, you need to use your pi's. You need to use the math palette. Don't be approximating. Don't approximate anything unless you're directed to. When students say that's not clear, I completely disagree. If it does not say to approximate, then you don't. That's the direction right there. If it says approximate, it will tell you the number of decimal places or round to the nearest integer. I think you're getting really good at that. But again, remember, always exact unless otherwise directed. Now you're thinking, well, this is not good, and at least in the sense that we've got extra multiples of 2 pi and it's negative. So what we want to do first is get rid of the extra multiples of 2 pi and then make it positive. So any order is fine, but it's probably easier if you get rid of the excess 2 pi first. So now t, go ahead and divide by 3. So this is, let me do a little sidebar here like I did here. That'll help you. 11 divided by 3. This would just be 3 plus 2/3. So that's the division algorithm like we did for polynomials that nobody seemed to like. So now we get negative 3 pi minus 2 pi over 3. Okay. Now notice we've got a negative 2 pi in here. So that's really a 0. So let's say this equals negative 2 pi minus pi minus 2 pi over 3. And I'll use the congruent symbol. That's a multiple of 2 pi. So that's just a 0. So we get negative pi minus 2 pi over 3. Now what we want to do is add a multiple of 2 pi to make it positive. This is negative. So now this will be, we'll just add 2 pi to it. It's not going to move it anywhere. It's still going to terminate at the same place. So we have negative pi minus 2 pi over 3. So we get pi minus 2 pi over 3. So notice when we put this into the positive category, the negative pi absorbs into the 2 pi and we get pi minus 2 pi over 3. But that's just pi over 3 because that's 3 pi over 3. This is pi over 3. So what we're seeing here is that these have the same terminal points. These terminate in the same quadrant, and that's in the first quadrant right there. So the idea is you do this computation to basically do what we did up here. This didn't take much time because it was already positive and it didn't have any multiples of 2 pi in it. So that was easy. To figure out 3 was just one simple computation. Here we say, okay, let's get rid of the extra multiples of 2 pi and then make it positive by adding 2 pi. Once we have this, now we can apply the formula for the reference number. Well, again, t terminates here in the first quadrant, so its reference number is itself. So this implies that t bar is just t, which is pi over 3, in the sense that these are equivalent. So we're saying these are equivalent modulo 2 pi. So when I say equal here, I'm saying equivalent. And that's what we have to get used to in trigonometry. So an equivalence here. So the thing is that here we notice that we lived in the third quadrant. So we had to apply a different arithmetic to compute the reference number. Here we're already in the first quadrant, so we're done. And now, of course, we did our unit circle. So what's the corresponding terminal point, since we even know it? This will just be what? Now in the previous one, yeah, sometimes I'll put the P out front. If I don't get mad at me. It's a lot of times I'll put the P out front here. So if you want to go ahead and replace the P there, that's probably better notation. And then this will just be the flip of that, 1/2, and then the square root of 3 over 2. So when we can, we'll go ahead and write down the terminal point. Sometimes you may just be interested in the reference number, and then we're going to need a few more identities to actually get at the terminal point in a more precise way. Now, what I wanted to do here, we've got in the WebAssign, we've got some nice examples about the reference number. Well, we're not really interested in the terminal point, but I want to give us a little bit more practice with reference numbers. So here's an example. Again, exact calculation. And I'm going to show you some 2 decimal approximations for the axial representations of pi that will be helpful when we're trying to figure out the terminating quadrant if we have a t that has no pi's in it. So for instance, say we have t equals 5 pi over 7. And again, we want to compute t bar exactly. And all this means an exact computation. So now we're thinking, okay, well, when you think about this, we think about the axes. We have the 0, we've got the pi over 2, we've got the pi, we've got the 3 pi over 2. Just kind of write these down just to kind of get your bearings. And then just say, of course, if we live in here, we're in the first quadrant, second quadrant, third quadrant, fourth quadrant. So that's the logic that we're using. And so now you're thinking, okay, well, you know, this is probably somewhere in here, but where is it exactly? So let's just look at pi over 2 and compare. I mean, this is kind of crazy arithmetic. If we had doesn't divide, but 2 divides 7 3.5 times. So 3.5 times pi. Well, that's bigger, okay? And then if you look at pi right there, pi is just 7 pi over 7. And 5 is between those two numbers. So 3.5, 5 and 7. So now what we see is that because of this inequality, we see that this t lives in the second quadrant because it's between these two numbers. So this implies that 5 pi over 7 lives in the second quadrant. Okay, so just doing a little basic arithmetic here, we see where this actually lives. And so now t bar will just be pi minus t, 5 pi over 7. But that's just 7 over 7. We've already got that there. So that'll be 2 pi over 7. So there's the reference number. Now, of course, this is not on the unit circle, but we don't have to worry about that. We just need the computation of the reference number. So this is what I like about the WebAssign. You want an exact computation. Even if you use some approximating techniques like we have here, we can still determine the exact reference number. And that's exactly what WebAssign wants. So let's look at a couple more examples of this. I'm going to put this over here. So I thought these were interesting problems, and I want you to be in the know about them and not struggle with this concept, because this is all basic stuff, but you have to think it through. Now here, for this example, we have t equals negative 5 pi over 9. And you'll be doing a calculus 1 problem or a calculus 2 problem or calculus 3 problem where you have to use these ideas, and you'll be glad you paid attention in pre-cal. So now when you look at this, you're thinking, well, you know, I can't apply the reference number because this is not positive, but this doesn't have any multiples of 2 pi in it because it's smaller than 2 pi, even in absolute value. So first what we want to do is make this congruent to something positive where we can apply the formulas. So we'll say this is congruent to, and if you like, let's just say 18 pi over 9. That's our 2 pi is just 18 pi over 9 if we have a denominator of 9, since we kind of need that. I'll go ahead and write that. So that's the 2 pi minus 5 pi over 9. So now when we subtract 5 from 18 is 13. So we get 13 pi over 9. Okay, well, what is this? Well, let's just look at this. So now what does this equal? Let's do the same thing we did before. 13 over 9 will just be 1 plus 4 over 9, just using the division algorithm. So we get what? Pi plus 4 pi over 9. Now, this is where we think it's like, well, how big is this? How big is this? Well, it's not bigger than pi over 2. Let's see why. Because pi over 2, if we give it a 9 as a denominator, 2 divides 9 4.5 times. So this is 4 1/2 times pi. So this is bigger than that. So we don't breach the boundary between the third and fourth quadrant. So this means that this lives in the third quadrant. So this is not bigger than pi over 2. So we start at pi and we stay in the third quadrant. So that's our computation for that. So then, if this is in the third quadrant, we have t bar. Well, and I've already have that right there, so don't erase it. So this will be pi t plus 4 pi over 9 minus pi. The pi's absorbed, and we just get 4 pi over 9. So when you look at these computations, it's okay if you use some fractions here. You're thinking, well, I need to get a common denominator so I've got beautiful numbers. Don't worry about it. I've started thinking that my students can just say, okay, well, 4.5 is bigger than 4, so that's all I need. So the logic is just to basically figure out, where does this actual t live? Where does it terminate? But remember, the reference number requires a positive input. So we have to find the real number that lives in one of the 4 quadrants, where we're thinking 0 to 2 pi, okay? Now, here's one where we don't have a user-friendly number. Let me show you. So this is t, oh, let me get rid of this, I don't need that. I need an equals just hanging out. So we've got t equals -3. Now, what I wanted to do here was just give you some 2 decimal approximations of the axial measures of t. So we have a 0, and then we have a 1.57, and then we have the 3.14, which is what we usually think of when we approximate pi. And then we add that, that'll be a 1, a 7, a 4.71. And then, of course, if we double this, we get 6.28. So these are rogue pretty much, but these are 2 decimal approximations. So we have first quadrant, second quadrant, third quadrant, fourth quadrant. So if you got numbers that aren't very user friendly, you can use these as a basic approximation technique to figure out where this actually terminates. And that's a good way to look at it. So now we can say, well, you know, this is not positive, so we can't apply the formula. So now we'll say t is actually congruent to 2 pi minus 3. So that's going to be terminated at the same point, but it's going to be a positive. So now when we look at this, we can say, well, 2 pi is approximately 6.28. And we subtract 3, we get 3.28. So now with our approximations, we see that t actually lives in the third quadrant. So this implies that t lives in the third quadrant. Okay, so now when we apply it, we do it to the positive one. So then t bar would just be 2 pi minus 3 minus pi, which is pi minus 3. That is, pi from 2 pi is pi, and pi minus 3. So again, we can still utilize 2 decimal approximations to get the location of our t, our quadrant of termination, so to speak. And so once we verified that, then we can go back to say, okay, this is exactly what t is. It's equivalent to this. And so this is the positive that we need. We know it lives in the third quadrant. And so we apply the formula for t's that live in the third quadrant, namely subtract pi from t to get that. That's exact. This is exactly what WebAssign wants. So if you have a pi, you must type in a pi. You must use the math palette, just like any Greek letter that we use. The Euler E, the base E, you can just type E and that works fine. That's a big time savings. And I'm sure you all are finding shortcuts to getting symbols produced on your WebAssign. That's fine. I have students that come up with all kinds of shortcuts. They tell me about them. Oh, Professor Ron, I do this. I'm like, well, great. You know, share what you know. I think with frustration, everybody tries to find quicker ways to get things expressed. So that's fine. Now for D, we've got, well, here's another one. Kind of crazy, right? We got t equal 5. You're thinking, well, why did you do that one first? Why didn't you do this one first? It's so easy. Well, it is easier than this. This was a harder problem because it started out negative. But we have t equal 5, so we can go up here and say, okay, well, using our 2 decimal approximations, t lives in the 4th quadrant. So we're done with this. This is in the 4th quadrant. So then, no work to do here. No work to do here. Then t bar will just be 2 pi minus 5. And we're done. So the idea is if we can quickly establish the quadrant where t lives, that is, we've got a nice problem here. You can see how you can make these problems a little bit untoward. I'm not trying to make you think about this and say, oh man, these are tedious or whatever. I just want you to be able to work with multiples of pi and to be able to work with these numbers, because you might be in a physics class or an engineering class and you want to show your professors that you know how to work with this stuff. I mean, if you run right to a calculator, that's probably the worst indication that you don't understand what you're doing. So it's better to have understanding so you can use your calculator as a tool, not as an end all. If that's the first thing you pick up, then that's not good. Now, let's look at what do we do with all of this stuff? I mean, why do we care about any of this stuff? Well, we've got this nice unit circle. So now let's write down basically what the deal is. Why do we bother to talk about the unit circle? So I just basically summarized the 6 trig functions, the circular functions that we're going to get from all of this. And you're thinking, wow, look at this, Professor Ron. So, like I said, the unit circle just mimics distance along the unit circle, ladies and gentlemen, just mimics the real line. And so you're thinking, okay, all right, so the domain for our first 2 functions will be the real line necessarily. Okay, so here's what we're going to do. You're going to fix a t. You take some real number, think of it as measurement along S1 from 1, 0. That's how we established all of this. From that, there corresponds a point on the unit circle such that P is the terminal point of T. That is, T terminates somewhere when you measure along the unit circle. And that point of termination we call P, the terminal point P. So that's how we're going to define 2 functions. So for any T, we're going to let cos T be the X coordinate of the terminal point. Now cos T will be short for cosine, cosine. And if you've had some trig before, you've heard of cosine. I don't know. I think it's weird that we have these strange abbreviations and all, and they look odd, but in a few weeks you'll be very comfortable with these. Now we're going to define sine of t to be the y coordinate of the terminal point. So we have that input, which is the measurement along the unit circle, and then we associate with that terminal point, that is the termination of t, the actual terminal point, and for the sine, we associate with it the y coordinate. And so these are 2 functions that are unambiguously defined, because for every t, there is a unique, what? Terminal point. So, wow. That was, but then you're thinking, what what kind of functions are these? We've defined them with the unit circle, so they're very abstract. It's not like y equals x. The computation of the trig functions is therefore more complex. And so we actually term them transcendental since they're not really based on the standard algebraic manipulations that we're accustomed. Just like the natural log or the base A log and the base A exponential, though they do have algebraic properties, they are not algebraic functions. They are actually transcendental functions. And the whole idea stems from the fact that pi and e are not solutions to polynomial equations with integer coefficients. That's the definition of transcendental number. So if that makes any sense, fine. If it doesn't, it doesn't matter. So now you're thinking, okay, so boy, talk about making a whole lot out of basically nothing. So now we think of all the positive numbers being mapped out this way, and then all the negative numbers being mapped out this way in the clockwise direction. Now, if we're saying that the cosine t is the x coordinate, we're seeing that the biggest the x coordinate can be is 1, and the smallest it can be is -1, just using the unit circle. And then for the y coordinate, the largest the y coordinate can be is 1, and the smallest it can be is -1. So you're thinking, wow, the domain of sine and cosine will be all real numbers, but the range is only -1 to 1. We call these bounded functions. We rarely have worked with any bounded functions unless we just restricted the domain so that it didn't go on forever. So the sine and cosine are functions that are bounded between the real numbers -1 and 1. So if someone says solve the equation cosine t equals 5, you'll say no solution. And then they'll say, why? Are you a math genius? No, I'm just taking Professor Ron's pre-cal class, and 5 is not in the range of the cosine function. Okay? So now it's kind of like the exponential, base A exponential, ladies and gentlemen. The output is positive. Okay? So if someone says solve 2dx equal -1, you'll say no real solution because the outputs don't make sense. So it's the same thing here that we've been doing. So now you see that this unit circle has actually created something of interest to us. And you future STEM professionals probably have already seen this in action in your science classes, namely physics, which you're going to take more of, in your engineering classes, which you're certainly going to take maybe too many of, but you want your degree, so you'll do what you're asked to do. So we've got these two functions, and you're thinking, what did the smart people decide? Well, they decided that they want to take combinations of sine and cosine, or manipulate the sine and cosine to produce 4 more functions. And you're thinking, well, we're fine with sine and cosine. Well, again, this was not something that was determined overnight. And of course, this would make a great history project. But what you're seeing here is that we have found that the 4 other combinations are actually very useful. The first one looks like this, ladies and gentlemen. We take now the ratio of sine to cosine. That is, now sine t will be y over x. We take the y coordinate of the terminal point, and we take the x coordinate of the terminal point, and we get y over x, which is sine t over cosine t. And so that's how we define tangent t. But then you're thinking, this function is going to have vertical asymptotes because the cosine t can be 0 when you're at the axial representations, odd representations of pi over 2. So when you're up here at multiples, odd multiples of pi over 2, here and here, the cosine is 0. So you must exclude the odd multiples of pi over 2 from the domain. So these become vertical asymptotes. Now, I'm using n as the integer, z, element of z, and 2n plus 1 is by definition an odd number. It's not a multiple of 2. And then, of course, with the vertical asymptotes, the function becomes unbounded and you get the full extent of the real line for the range. We'll say more about this when we start graphing these things. Now, another thing that came to mind with all of these smart people that decided we need to define another function, they said it will be convenient to write the reciprocal of tangent. Okay, what happens if you reciprocate tangent? Well, y over x becomes x over y. And then, of course, that's just 1 over tangent, if you want to think about it that way, 1 over tangent. But then that means that you get cosine t over sine t. And then, of course, if that's the case, zeros of sine must be excluded. And then, of course, you go back to a unit circle and remember that sine is 0 at these axial points. So if you're at multiples of pi here, multiples of pi, the sign is 0. So you must exclude integer multiples of pi from the domain of the cotangent. So what we're seeing in this particular case is that we're getting the existence of vertical asymptotes with these new trig functions. Sine and cosine are fine, no problems, all real numbers, just coordinates of the unit circle. But when we start taking ratios, we do get zeros in the denominators that aren't zeros in the numerator because the zeros don't correspond between sine and cosine. We can see that from the unit circle. And so now, again, we get a range of all real numbers, but we limit ourselves to excluding, in this case, multiples of pi. So the last two, again, you may think, okay, well, somebody thought about this because, you know, what's the use of this? Well, again, the mathematics and definitions stick around because of their utility. And so it was very convenient to think of reciprocating the cosine function. So we call that the secant. So if we reciprocate cosine, we call it the secant function. That's 1 over x. And now, of course, if we go over here, over here, we have to remember that we do not want to divide by 0. So just like the domain of the tangent, we have the same domain for the secant. But here's the issue. With that bounded function -1 to 1, when you reciprocate it, you basically lose those real numbers except the 1 and -1 in the range. So the numbers between -1 and 1 get kicked out when you actually reciprocate the cosine function. So you get a nice domain with an omission in the middle, symmetric to the origin. So you're thinking, look at this, Professor Ron, all of these domains are symmetric with respect to the origin. Is that going to help us out with even and odd? And of course it is. It's going to be why we get even and odd for all of these functions. Now, for the next one, and maybe an important one, ladies and gentlemen, we think, okay, well, if we reciprocate cosine, can we also reciprocate sine? Yes, and we call that the cosecant, cosecant. So secant, we use SEC, and for cosecant, we use CSC. This can be confusing at times, and to write, you know, I usually print the cosecant and print these because to try to do them in cursive, they don't always look very nice. So, but you work on what is best for you. Again, we don't want to divide by 0. So when we look up here and think, okay, we don't want the sign to be 0. So again, we must exclude multiples of pi. But just like we have over here, the range will omit the numbers between -1 and 1. Just like we had for here. Again, upon reciprocation, these numbers are lost in the range. Now, one thing I want you to be aware of, just like working with identities with logarithms, we can get very creative with trigonometric representations. For instance, we know tangent is sine over cosine, but let's just reciprocate everything and write it as secant over cosecant, because this is 1 over cosine divided by 1 over sine, which is sine over cosine. So it may be of use sometimes to write tangent this way. And with that in mind, you could write cotangent as cosecant over secant. when I do trig integrals in Cal 2, it's sometimes convenient to think of these representations to make the computations easier, because everybody says, well, let's just convert to sine and cosine. I'm like, well, you know, that's going to take that'll take a time, that'll take a while. Why don't we just use some relationships that are simple and that will move the problem forward? So again, just remember, very simple ideas that we've talked about today, but when you start putting them together in concert, there's a lot to think about. Not difficult, mind you, but the synthesis is the difficult part, putting all the elements together. Now, one thing I want to discuss next are the Pythagorean identities. Now, when it comes to actually writing these, I'm going to go ahead and state them. We just go right back to the unit circle. And then I will mention something about the even and odd that we get for free. So remember that x squared plus y squared is 1. That defines the unit circle. But now we have replacements for x and y. That is, now we can say x is cosine t and y is sine t. Now you're thinking, okay, well, this is what is termed the fundamental identity of trigonometry. That is, when we look at this, we think, okay, cosine squared plus sine squared equals 1 for all values t. But this is not the standard notation. What has been developed is to have a more relaxed notation. That is to say cosine superscript 2t, or cosine t quantity squared. This is the shorthand which has become very much in favor, and it's very easy to use and easy to spot. We don't really do it so much with logarithms, even though some students will do that. I don't think it's done as much, but with the trig functions, it's standard fare. So we're lazy, so we like this shorthand notation. That is, we could say cosine of the quantity t squared. This is very different. This is basically saying that when you have cosine superscript 2t, that's writing that, cosine of t quantity squared. Same thing for sine squared. We'll be lazy and say cosine squared means that. Sine squared means that. That's just the shorthand phraseology, which will become very useful to us. And since these Pythagorean identities come up all the time, we need a quick way to write them, okay? Now, this is, like I said, these are called the Pythagorean identities. Identities. Pythagorean identities. Now, another form which is equivalent to this, we can just now divide through by cosine squared and develop another form that's of use to us using secants and tangents. So we get 1 plus tangent squared, because we've got sine squared divided by cosine squared will be tangent squared, and 1 over cosine squared we can write as secant squared. So this shorthand notation will become very familiar to you quickly because it's widely used. Now again, with the WebAssign, if they build in parentheses, don't delete them, go ahead and close them. It just really depends. I mean, you can use superscript, the little caret, and type your trig functions that way, but you choose whichever method you like and feel most comfortable with. But do not delete any leading parentheses from the WebAssign, because then it won't like that. So be sure that if you're typing something where you've got a leading parenthesis, that you close it. If you're deciding to use parentheses, then you must obey all of them. Now, the third one would be, for instance, if you wanted to just divide by maybe sine squared. So you get a 1 plus a cotangent squared equals cosecant. And you're thinking, okay, well, that seems to be a lot. Is this useful? Absolutely. These are all very useful in their respective forms. They all say the same thing, but they're very useful. And remember, an identity is an equation that is true for all values of the variables for which it is defined. This is defined for all real numbers. But when we start looking at this, we have to be a little bit more skeptical because we have to throw out values that make the cosine zero. And here we have to throw out values that make the sine zero. Clearly works as long as we, have definition. So remember, an identity is an equation that is true for all values of the variable for which it is defined. And if you have more than one variable, you just say variables. So these are the Pythagorean identities. And I'll just say very useful. I mean, these are like what we call the fundamental identities, and we'll go back to them over and over and over again. Now, one other thing that I've already mentioned, we have these nice symmetric domains. And by the symmetry of the unit circle, it is no surprise that the cosine function is even and the sine function is odd. And then by definition, we get that the secant is even and then the other three are necessarily odd. And I'll show you a little way to actually come up with that. A rigorous proof utilizes the reference number, and maybe a cheat proof would be like a drawing, which we'll take in a pinch. So now the even functions, again, all of these domains are nice and symmetric relative to the origin, so we don't have to worry about checking that. That comes for free. So domains are symmetric. No problem there. We get that for free because of the unit circle. So we get that for free. And now the even functions will be cosine t and secant t. The odd functions will be the other four: sine t, tangent t, cotangent t, and then the last one, cosecant t. So basically what this means, that is cosine of the additive inverse of t is cosine t. Secant of the additive inverse of t is secant t. The negative absorbs, just like we had with the algebraic functions. But here it's more symbolic. And if you don't respect it, you do extra work. Okay, so these are extremely important. Sine of the additive inverse of t will now be the negative of sine t, the negative factors. Tangent, these are, wow. They in Wikipedia, they call it the tangent of the negative angle. I mean, Wikipedia, though it gets a bad rap, it's a free, it's free, and everybody says, oh, don't use Wikipedia. Well, trust me, ladies and gentlemen, I found many pages on Wikipedia that I found to be very useful and give excellent information. I remember when I was trying to do an honors lecture and I needed some extra inverse trig identities, I found a whole slew of them, and they were all correctly motivated. I thought, well, that was free and great for Professor Ron. So it's not, if people start knocking it, don't. I mean, there's plenty of good information there. And so cotangent of negative t is negative cotangent t, and then cosecant of negative t, or the additive inverse, is the negative of the cosecant of t. So the even and oddness we basically get for free. Now, actually proving this part you can do with a picture, quadrant by quadrant. In order to prove these, you have to go quadrant by quadrant. So in order to get any of this, you just prove it for sine and cosine, then you get the others for free because they're built on sine and cosine. So you only have to actually do 2 proofs, and I'll show you a little bit about that. But this, commit, 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 commit to memory, because you know it. These, commit, commit to memory. The Pythagorean identities. They are so useful, and they will make your work easy when things get tough and you need to simplify your work. The Pythagorean identities are where it begins. And then of course we get these basically for free with a little bit of work. Now, what I want to do is to look at a couple of examples where we basically just say, okay, now that we've defined the trig functions, we know their values, at least relative to the what? The S1, the unit circle. So let's do some computations. So we've got t will be the negative 3 pi over 4. Now again, the reason I went ahead and gave you the even and odd is that we can use these properties when we're using negative arguments. They're going to make our work a lot easier. And so here's what we want to compute. So we're going to compute sine, we'll start with tangent of t, cosecant of t, and cotangent of t. Now, remember, and this is very important, in order to move forward with all of these, you can think, well, I can use my unit circle for Professor Ron's unit circle and be done with this. But I want to actually help you to do this via the reference angle. So now what we can do when we look at this is to move this to the positive realm. So we can say t equals negative 3 pi over 4 equals 2 pi minus 3 pi over 4. Now, when you look at this and you think about this, you're like, okay, well, this is a negative angle. It has no multiples of 2 pi in it. And now when we look at this, we have exactly what we need. That is, we've got a positive angle, and we just need to figure out where it lives. Now, first, let's just go ahead and do a little bit more work here. Notice if we get a common denominator of 4, we get 8 pi over 4 minus 3 pi over 4. And that gives us 5 pi over 4. Now, of course, you're thinking that's on the unit circle. But when you look at this and you think about how big this is, what is this? This is just pi plus pi over 4. 5 over 4 is 1 plus 1/4. And this lives in the third quadrant. So you move from 0 to pi and then down some. But you do not breach the boundary between the third and fourth quadrants. So this gives you the actual definition. So now notice here in the third quadrant, x is negative, y is negative. So this implies tangent t is positive. Okay, so we know that in the third quadrant, the tangent must be positive because the sine and the cosine are both negative. So now this means, okay, so what's t bar? T bar will now be the t pi plus pi over 4 minus pi, which is pi over 4. So tangent of negative 3 pi over 4. Let's just see what we get. Now notice we've got all of this stuff over here, so we can just move to this. We can go from here all the way to here. So we take the positive, so we don't do anything. If you like, let me just say this. If you were going to think about it this way, let me add some extra stuff here. This would be the negative of tangent of 3 pi over 4. Okay, and then when you look at this, you're thinking, well, what is the actual reference number? So let me finish this just in a second. I'm going to use what I have here. Tangent of negative 3 pi over 4 is now equivalent to tangent of pi over 4, and it's positive. which is 1. So basically here, I avoided using any of the odd properties here. Here, I just worked through it, know that my tangent needs to be positive, and so I get my reference number here. And so whatever value this is, I can append it to this by taking the correct sign here. So the tangent of negative 3 pi over 4 will just be, in this case, tangent of pi over 4, which is 1. Now, if I use this approach, let me go ahead and fill this in. Here's another way to do it. I can say, okay, well, notice here, this is where? This is in the second quadrant. Here, x is negative and y is positive. So this means that tangent, in this case, of 3 pi over 4 is negative. And now what is t bar in this case? We have a separate t bar. T bar will now be, if you look at it, this will be pi minus 3 pi over 4, which is pi over 4. So now we get the negative of the negative of tangent of pi over 4, which is tangent of pi over 4, which is 1. So this would be another way to do it. Since I went ahead and mowed through this and did it this way, I didn't have to worry about the negative here. I went ahead and dealt with it first. But if I don't deal with the negative and just say I'm going to use the fact that it's odd, I can factor it and then operate on this. So I'm in the second quadrant. So therefore, the reference number will be pi over 4, but the tangent in that quadrant is negative. And so now when I replace this t bar here with the, when I replace, excuse me, the t with the t bar, I get the negative of this, which is made negative by that negative. Now, some students will say, well, I understand this. It's a little bit quicker to go this way. But if I go this way, you avoid completely the use of the odd function tangent. So you have many, many ways to do this. Now, here's the third way. You're thinking, I've got Professor Ron's unit circle, and I could say negative 3 pi over 4, which is clockwise to here. And then take the ratio of these two negative numbers and get 1. So the third way is just to say, I feel lazy today, and I'm not going to be a math professor like Professor Ron. So I'll just say, okay, negative 3 pi over 4 is clockwise to here, and you're done. So the idea here is you can use the unit circle as a visual, which is fine as long as you've got something on the unit circle, or you can utilize the techniques here. So I want you to be able to do both, but I don't want you to think that you have to do it any one way. I just want you to be aware of how to maneuver here. So if we don't use the oddness of the tangent function, we go here to here. If we use the oddness, we go here. So I'm giving you plenty of ways to actually do this that hopefully you can find something that works for you. Now let's look at another one. Let's finish the problem. So now we have tangent of negative 3 pi over 4 equals 1. And so this implies that the cotangent, this is the easy part, negative 3 pi over 4. It's funny when I work a problem, if I work it a certain way and I don't utilize something I just told you, I'll be honest with you and say, okay, I'm doing it this way. And that's what you have to do when you do the trig. You can't, you have to follow the logic that you've set up. And that's how you become better at math. Now, of course, this is just 1 over tangent of negative 3 pi over 4. And we just found that to be 1. So this is 1 over 1 or 1. Or you could just omit all of this and say cotangent is the reciprocal of this, and the reciprocal of 1 is 1. Now for cosecant, now we'll use what we already have. We don't have to start over. So I'll just go ahead and use what I've got over here. Notice at this point, we get a reference number of pi over 4, and this is in the third quadrant. So remember, in quadrant 3, we have the cosecant is less than 0. So this will be negative cosecant, and we'll use the reference number pi over 4. So this will be negative 1 over sine of pi over 4. So this is negative 1 divided by 1 over root 2, which is negative root 2. So the idea here is that you have many, many, many ways to work these problems, and they must be worked exactly, okay? So if you've got a situation where you're using the unit circle, you have everything exact. For instance, you could just say, okay, well, negative 3 pi over 4, that'll take me here. So I reciprocate the y coordinate and get negative root 2. That's one way to do it. You can look at the fact that you already determined the reference number dealing with the negative angle here, right here, and also utilize the fact that in the third quadrant, the cosecant is negative, and get that. So you have many ways to do these types of problems. Now, one thing that's very, very useful, and you'll get plenty of opportunities to practice this with your WebAssign. Now, it's called using the Pythagorean identities to rewrite one trig function in terms of another. And this is what you do a lot in Cal 1 and more so in Cal 2, and then also in Cal 3. So for instance, here we go. Write tangent t in terms of sine t. Now, here's the thing. We need to know where t terminates. So when we look at the 4 quadrants, we know that for each quadrant, the trig functions have different values. And so if we want to be precise, we have to get a precise algebraic expression for tangent t in terms of sine, we have to know where the t terminates. If not, then we only have up to a plus or minus sign, okay? So now remember, in this quadrant, this is the 4th quadrant. Remember, x is positive, y is negative. So this implies that tangent t must be negative, since it's the reciprocal of a negative and a positive. So this must be negative. So now we're good to go. So tangent t, let's just write the definition of it. This is sine t over cosine t. Now, what's nice about this is that the sine t is going to carry the sine of the tangent, so that's already taken care of. The sine t is less than 0 in the 4th quadrant, and we know the cosine is positive. So at this point, all we need to do is use Pythagorean. So we have cosine t. So we have sine t, and we're going to take the positive square root. So this will be the positive square root of 1 minus sine squared. That is, we've used cosine squared plus sine squared equals 1 if and only if cosine squared t equals 1 minus sine squared. And then we extract the positive square root because in the 4th quadrant, the cosine is positive. And so we're done. So this gives you, these are quicker than the arithmetic approaches. I mean, the thing is that you must master all of the approaches to really know what you're doing. But I would prefer that you only use the unit circle just as a reference and not as an end all. It can be a good tool, but you should be able to work with the first quadrant and be able to recognize what you need otherwise. Now, let's try another one. Let's say that we want to write, here's an example, and then we'll do compute some values. Let's write secant squared t, sine squared t in terms of cosine. Now, of course, this is non-negative. This is never anything but non-negative. So t is in any quadrant. So t corresponds to any quadrant. No need to worry here. This is always going to be non-negative. This can be positive, 0, or negative. So we don't have that luxury here. We need this. Here, this is always non-negative, so that doesn't really matter where t lives. And if you tell us where it lives, it's not going to impact the calculation. So now, in terms of cosine, so secant squared t, sine squared t. First, secant squared is just 1 over cosine squared. That's just definition. And now, of course, we can use the Pythagorean identity here. We can just write sine squared as 1 minus cosine squared. So use Pythagorean right here. 1 minus cosine squared. Now, of course, Webasine would take this. There's nothing wrong with this, but you can multiply through if you want. 1 over cosine squared. And then, of course, cosine squared over cosine squared is 1 with a minus sign. So again, we see that the manipulation of the reference numbers and all of that is still part of what's going on here, but in a more arithmetic way. We're not basically manipulating specific numbers, but we're keeping track of signs. So when you think about the unit circle and you think about how we have utilized the unit circle to define 2 fundamental functions, namely cosine and sine, we are tied to the unit circle arithmetic to be able to make all of this work. And if you ignore it, then you get burned. So again, just remember, you can make up problems here. And I would encourage you, once you finish your Webasine, just to make up some problems and try reference numbers and try computations. Again, you're going to have to get used to the unit circle, but it'll be very easy because you do the same thing every time. You just must be true to the course. If you start your logic in a certain way, you complete it. You'll start to work a problem and think, oh, well, I could have done it this way. But, you know, that's just how math is. Math is very gratifying because there are many ways to do problems. Now, another type example that we can do, you're thinking, if we can figure out algebraic expressions, what about values of all 6 trig functions if we're just given a little bit? So for instance, we'll just say find all trig values. Find all trig values. Say for instance, we're given sine of t is -5 over 13. Now when you see that, you're thinking, okay, Professor Ron, we could be in the 3rd quadrant or the 4th quadrant. Again, we could be here or here. We need more information. So the next piece of information that Webasine gives us is that t terminates in the 4th quadrant. Now you look at this and say, well, that makes sense, but now that tells us all the other stuff. We know sine is positive, but this just says that cosine must be, sine is negative, so cosine is positive in the 4th quadrant. So now what we see is, if this is the case, this will determine all of the signs. So we're thinking this way: x positive, y negative in quadrant 4. That's all we're doing. So now you're thinking one use of Pythagorean, and then we can coast. So let's go ahead and find cosine t. So cosine t will be the positive. So we do principal square root of 1 minus sine squared. Notice the use of the sine squared, very beneficial, very easy to write. We know it means sine of t quantity squared. So I'll use the brackets. So 1 minus negative 5 over 13 squared to the 1/2. So this will be 1 minus, so that'll give us 25 over 169. Nice, easy numbers. Symbolic computation is easy when the numbers are easy. And so we get 169 minus 25 over 169 to the 1/2. And now, of course, the 5 from the 9 will be 4, and the 2 from the 6 will be 4. So that gives us 144 over 169. These are both perfect squares. So we get 12 over 13. So basically, when you're doing these problems, you'll need one application of a Pythagorean identity, and then the rest will just be using the definitions. So now let's go ahead and reciprocate everything. Cosecant will be the reciprocal of sine t. So that'll be 1 over negative 5 divided by 13, which gives us negative 13 over 5. And the secant will be the reciprocal of cosine, which will be 1 divided by 12 divided by 3, or just flip it in your head, 13 over 12. So again, when we look at all of these here, we see, okay, cosine's positive, secant's positive, sine is negative, so cosecant is negative, and then of course that means cotangent and tangent must be also negative. So let's go ahead and compute these. So tangent t will be sine t divided by cosine t. So we have negative 5 over 13, and you can go ahead and flip this. That'll just be 13 over 12, and this gives us negative 5 over 12. So tangent t, again, is easily computed just by using the definition of sine over cosine, and then reciprocating the cosine, and we're good. And then, of course, this implies that cotangent t is just 1 over tangent t, the reciprocal. Go ahead and remind yourself what it is. And so you reciprocate this and get negative 12 over 5, just skipping that step. Once you finally kind of see all of this, remind yourself what you're doing. I would say this, you'll get very familiar with these identities very quickly. So don't feel like you have to write out 100 steps, but don't write out so few steps that you can't really go back and check your work. Because simple mistakes here, again, I may be making a big deal about how you make these computations here, but inability to do this kind of arithmetic, ladies and gentlemen, will be disastrous. You will never move to the next level of understanding if you don't understand these kinds of computations. It is important to be able to maneuver the arithmetic of the unit circle. It's imperative. Now, what I want to do is say a little bit about the even and odd bit, though, since I kind of waved my hands over it. Let me give you a little more ideas behind that. So, say for instance, we've got this like a little lemma. We'll just say this lemma. And you can go ahead and start recording values of sine and cosine or tangent. That a lot of times students will write additional values on the unit circle. Feel free to do that. But here's a lemma. We can say cosine t is even as an even function, and sine t is odd. Now, what I wanted to do was just give you like a little visual of this and then show you how you might do it more rigorously using the reference number and the quadrants. So you're thinking, I would basically just have to show this true for all four quadrants because the cyclical nature of S1 doesn't require anything past that. So let's just look at the cosine. So if we said T lives in the first quadrant, so we have to show that for every value of T, that cosine of the negative of T equals cosine T. So first, if T is in the first quadrant, then by definition, the additive inverse of T is in the fourth quadrant. So when you think about the way we've defined these, and we see, for instance, well, let me just show you. So for instance, we have 0 here. I mean, the funny thing is that a lot of times when I say it's obvious, it might not be obvious. And then you say, well, then this says that now negative T, where's negative T going to be? So you multiply through by a negative, you have something like this. So this just says what? Negative T is, in this case, less than negative pi over 2, or greater than negative pi over 2, less than 0, which just means negative T is in the fourth quadrant. So that's what I meant by that. So again, if T is up here, negative T is down here, just basically because when you define the negative angles, you start here and go this way. So 0 to negative pi over 2, like we had negative 3 pi over 4. So you have to respect the orientation of the circle. So again, if T is in the first quadrant, the additive inverse of T is in the fourth quadrant. Okay, so you're thinking, all right, what is that? So what do I do here? How do I fix this? Well, this is negative. This is less than 0. So now this implies, let's make it positive. 2 pi minus T is now positive, but it also lives where? In the fourth quadrant. So when we look at this and we think about reference number, that's no good. That's no good because reference numbers cannot be applied to values of T that are less than 0. And by hypothesis, this is clearly less than 0. So we say, all right, so now when we look at this, we add 2 pi to this to make it positive. So again, now we're thinking of counterclockwise, but of course, adding 2 pi, we still terminate in the same quadrant. It defines the same terminal point. And so now this implies that, and of course, when we look at this in the fourth quadrant, we know that cosine, I'll just write this out, is positive, to not introduce any more notation. So now we say T bar, in this particular case, the bar of this, negative T bar, will now be 2 pi minus 2 pi minus T. So now if you're in the fourth quadrant, we subtract the actual value of T from 2 pi. So the 2 pi is absorbed and we get negative of the negative T of T, which is T. So now we see that, again, cosine is positive in the fourth quadrant. So we get cosine of the additive inverse of T is now the positive of cosine of the reference angle of negative T. But the reference angle of negative T is T, and we get cosine T. So for this quadrant, we have proved that cosine is even. Now you're thinking, that's a lot of arithmetic, but this is arithmetic I've taught you today. Now you're thinking, what's the quick way to do this so I don't lose my sanity, because I don't want to become a math major, or maybe I've inspired you to become a math major. If you don't like the computation that you do in math classes, except for the fact that it's going to make you an engineer, you're not alone. I teach very few students who have the ability to do abstract math. But if you find that you think you want to do that, let me know, and I'll make sure that you get focused in the right courses when you go to the university. I know most of you want to be STEM professionals. You want the glamorous life. So now let's draw the circle here. We'll be done. So here's a nice visual of this. And I kind of started out by doing this. So say you have a t value here that goes to here. So this is t. So we're saying t, let me write this, t is in quadrant 1. So this is a picture of what I just proved. So now you have p, just one more minute, xy. And then if you do negative t, so this is in the first quadrant, we're right down here. So this is negative t. So here, notice we have first quadrant and fourth quadrant. So by pictures, we're verifying basically what I've done here. The picture is not a proof, but it's mimicking what I've done here. And notice this will be the point Q, but it will have x negative y like we had before. So then you're thinking, oh, I see. So now this implies, at least by picture, that cosine of negative t is equal to x. That is we just take the x coordinate of the terminal point, but that is also the cosine of t. So that's the picture proof, which is not a proof. Okay, that's like a cheat proof, which is kind of intuitive. So what I wanted to show you was a rigorous proof of one quadrant and then a picture proof. The picture proof is worth a lot, and in the sense it's worth a lot of intuition, but you have to make it more rigorous than this. I mean, the picture, you can draw it and say, well, yeah, that's where negative t is. It would be in the fourth quadrant, but you have to prove that it's there. And then you actually have to prove arithmetically that this actually equals this. But as you get better and as you get more adept at doing this, you'll be able to move from here to here. So let me just make a comment here. The trigonometry is steeped in arithmetic. We do arithmetic on top of arithmetic. You must master the arithmetic of the unit circle. And once you do that, you can talk about graphs, you can talk about inverse trig functions and all that good stuff. So start making charts of all the values, use your unit circle, make notes, write down all the identities, write all the specific techniques to find reference numbers and use those to compute values, and enjoy this. And remember, unless an approximation is requested, we go with exact, okay? Now, like I said before, I'll put up an announcement for the next test, and everything that we do through this week will be fair game, but certainly anything that we do next week before the test will not be covered. Thanks for your attendance, and please stay safe and stay dry. Thanks, everyone.
Thank you.
Bye.
Bye, thank you.
Bye. Well, you have to enjoy math if you're going to do it.